difference between the 2 points on the pipe where the two arms of the manometer are attached is 0.20 meters. Determine the differential height between the two fluid levels of the two arms of the manometer. What is the height difference there? That's what he is asking. That means what is the pressure difference between those 2 points? So we need to consider 2 points. Let us take corresponding to this, that as point 1 and this as point 2. Let's say it is all one streamline. We can apply Bernoulli equation between those two, which will solve this problem. In case you have a doubt, the density of water is 1000 kilogram per meter cube, and the density of air, because we are dealing with two liquids here, is equal to 1.180 kilogram per meter cube. If it is not given in this problem, don't worry. If it is given in the exam, you will be given with this data. All right. And now applying Bernoulli between the two, P1 over rho g plus V1 squared over 2g plus Z1 equal to P2 over rho g plus V2 squared over 2g plus Z2. The velocity of the air is given. Let's call that as V. The rate of flow of the velocity, V dot, is given as equal to 65 liter per second. This we need to convert into meter cube per second. You know, (1,000 liters), in case you have confusion, 1,000 liters is 1 meter cube. Therefore, 65 liters is 65 over 1,000 meter cube, which will be 0.065 meter cube per second. That is the flow rate. It is the flow rate. But the flow rate is area of cross section times the velocity, because area of cross section times velocity gives you at any given section the volume, and that velocity is meter per second. Area of cross section times distance is volume, but if instead of distance you use velocity, meter per second, area times meter per second gives you the volume. So that volume can be written as A times A1 here. If you call that cross section as A1 and the velocity is V1, A1 times V1 is equal to that volume rate, which is 0.065 meter cube per second. From this, V1 is equal to V volume rate divided by area of cross section, which is 0.065 divided by the area of cross section there is he gave you, it is 6 centimeter diameter. So 6 centimeter diameter means the area A1 is pi over 4 d squared. So pi times d1 squared, which is 6 centimeters is 0.06 squared over 4. That is the area. So from this, the velocity at point 1, v1, because it's the same velocity in that duct, is equal to 22.9926 meter per second. So we know velocity at 1, pi d squared over 4, isn't it? Or pi r square, because r is equal to d over 2. D over 2 squared becomes d squared over 4, pi d squared over 4. It's pi r squared. But we also can calculate the velocity at point 2 by using what we call as continuity equation. Do you remember what it is? Continuity equation. The total mass of the fluid that is flowing should be the same at any section. Otherwise, if there is a variation in the mass flow rate from one place to the other place, what would happen? There will be accumulation of liquid, and that leads to swirling and confusion. And we are assuming steady state conditions, means whatever is coming is whatever is going out. Nothing is getting accumulated or stagnant anywhere. If that is the case, the total mass flow rate must be the same. Because it's a constant density, we are assuming mass flow rate also is equivalent to the total volume of flow at any given section must be the same. That means A1 at cross section A1, the velocity V1, A times V1 is the volume rate, must be equal to the volume rate at 2. Even if the areas are changing, the velocities will increase, but the continuity is maintained. So from this, can we calculate what is V2 then? Therefore, V2 is equal to A1 times V1 over A2. So which is equal to A1 is pi d squared 0.6 squared divided by 4 times velocity V1 we established 22.9926 all divided by A2 is again pi times what is the diameter? 4 centimeters. So 0.4 squared over 4. All right. Simplifying this, we get the velocity at 2 as equal to 51.7269. The velocity is increasing because the area of cross section is decreasing. All right. Once you know these two velocities, we are now back at the Bernoulli equation. One of the points you should take as the datum line. That means Z1 or Z2. Let's take the datum passing through point 1. So Z1 equal to 0. So if that is the case, the equation will reduce to T1 rho g. I'm taking pressures on the left side is equal to V2 squared minus V1 squared over 2g plus Z2 remaining there because Z1 is 0. I took V1 squared over 2G that side and P2 to this side, and that is the equation. So from this, P1 minus P2, the pressure difference is equal to rho times G times V2 squared minus V1 squared over 2G plus Z2. Substitute the known quantities, that is equal to 1.180 times 9.81, because air is the one which is flowing through that pipe, times V2 we know already 51.7269 squared minus V1 22.9926 squared divided by 2 times 9.81 plus Z2 height over Z1 is given as 0.20. In the problem that is given, can you see 0.2 meters height difference is there from the point where the two ends of the manometer are attached to. So that is what it is, 0.20. Z2 is at 0.20 meters above Z1. Solving this, we get the pressure. We are measuring the pressure difference from 1 to 2. That is equal to 1269.0526 Newton per meter square. This is the pressure, Newton per meter square. But this pressure difference is reflected in the height difference in the two columns of the manometer, which is based on water. So we know P1 minus P2 must be equal to rho GH. Therefore, H is equal to P1 minus P2 over rho G. But this rho is for the water. So that is 1269.0526, the pressure difference that we just calculated using Bernoulli, divided by 1000 times 9.81. From this, the height difference is 0.1294 meters, or H is equal to 12.94 centimeters. What do you think? We are using the Bernoulli equation, the continuity equation, A times V is constant. And then we are using the manometer principle to calculate the height through which that pressure difference can be reflected. Any question? Online? Any problems? Emerson Dewitt.
No, sir, no problems. Thank you.
Good. Any friends here? Can we just scan through anybody that can recognize?
Hi.
So online guys, anyone having the capability to turn on the video, this is the time. This is where we see friends and say hello. Anybody interested in turning on the videos? Oh man, you're sitting next door. So any friends here?
I don't know. We'll see who recognizes me.
All right. Where is Sam? Where is Wi-Fi? Is here. All right, guys, let's continue. Okay. You can still see the screen, isn't it? Can you still see the screen?
Turn on, turn on. Yeah, we can see you, sir.
Did they say? They can see? All right. Yep, it is shared. So that's how we can use. It's not very difficult, but at the same time, you just need to see what are the given conditions and what are the places where we can apply the Bernoulli, and then just use it smartly. Okay. And this problem I'm not solving now because I selected this as one of the model exam questions. I will solve it later on. I will solve it along with the model exam questions. And I'm leaving the last two problems here. The last two problems here for you to complete as homework. And this one I will solve. This I'm including in the model exam. I will solve later on. All right. That's all about the kind of problems we might get in one of the topics that we covered. So it's 1 week gone. Then the other 2 weeks that I have covered so far, one is the fundamentals of fluid mechanics, and the second one is fluid statics. So let's see some problems in the fundamentals of fluid mechanics before. Yeah. No. Yeah. All right. Let me save this. All right. And in that introductory lesson, that is one of the derivations that I told you as necessary. I will upload this for you to practice later on. And that is the other one. We discussed this. And this is the pressure in a bubble. And this is the height through which a capillary rise happens. I will upload this later on. And I have done some of these problems already in the class.